Let's look at the delta G of mixing for ideal gases. And so let's imagine we've got two ideal gases, A and B, and they're in a container. And let's imagine we have this frictionless piston. So the piston can move back and forth, but it separates the gases. And so we've got A on the left side and some other gas, B, on the right-hand side. And they're both at pressure P. Okay? And we pull out that barrier. We remove that piston. And so now we're going to have A and B mixed together in the container. And what we notice here is that because they've mixed, we now have A is able to move in the whole size of the container instead of just this little area over here, so its pressure is going to be lower than before. So it's not equal to the original pressure. And similarly, B was here, but now it's allowed to move in the whole container, so it's not going to be equal to the original pressure. In fact, we can go further than that and say that P, A, and B, while they're not equal, they're both going to be less than P. So the pressures of gases A and B have gone down. And we know from what we saw before that the change in chemical potential with pressure is equal to the more volume. And so if the pressure went down, the chemical potentials went down. So the chemical potentials for both gases went down. So we expect the delta G of mixing to be negative, right? In other words, we expect the gases to mix. Okay, so what is delta G of mixing? Well, delta G of mixing is just going to be G mix, or mixed, minus G pure. All right, so how do we calculate this? How do we calculate the Gibbs function of the mixed stuff versus the Gibbs function of the pure stuff? The key to this is to realize that if we add up the chemical potentials of each substance with the number of moles of each substance, we can get the total Gibbs function. So in our two-component mixture, if we take the chemical potential of B, which remember is the Gibbs energy per mole of B, and multiply it by the moles of B, we'll get the part of the Gibbs function due to B, and then we can do a similar thing with A. Gibbs function per moles of A times moles of A, multiply that. So if we add these two pieces together, we can get the total Gibbs function, which means, since we said delta G of mixing was equal to G final, which is mixed, minus G pure, we can rewrite this as the chemical potential of A pure, or sorry, A mixed plus chemical potential of B mixed, because that's the final state, minus the pure. So that would be NB times chemical potential of B pure, and then Na chemical potential of B pure. Oops, this is supposed to be A in the A term now. And we can simplify that a little bit by just pulling out the ends, right? So we have the number of moles of A, and then we just have mu mixed minus mu pure for A, and then we have a similar term for B, right? So just the amount of stuff you have, and then how much the chemical potential changed. So you can see that if the chemical potential of the mixed stuff is less than the chemical potential of the pure stuff, then delta G is going to end up being negative. The stuff's going to mix, which is what we expect. So really all we have to do is see what happens to the chemical potential of the two gases as they mix. That's the key to the whole thing. All right, so how do we find out how those chemical potentials change as we go from pure to mixed? Well, the key here is to remember that the change in chemical potential is going to be a function of the pressure. If we think about what's changing here of the gases, we said we were doing it at constant temperature. Let's just write out the whole thing for the change in chemical potential of the whole expression, the whole differential for the change in chemical potential with temperature or pressure. And we can see that we're not going to change the temperature. We said we were isothermal, so we just have to worry about this term, the VDP term. Okay, so the change in chemical potential is just going to be the molar volume times the change in pressure. So if we integrate, we wanted to go, let's do A. So we wanted to go from A pure to A mixed. And we have to integrate. Well, we said we started off with everything being at pressure P. So we're starting off at initial pressure P. And then in the mixed state, A is expanded to fill the whole container, so it's at some new partial pressure P sub A. So if we integrate this, we get the chemical potential of A mixed minus the chemical potential of A pure is going to be equal to, well, this certainly isn't constant because it's a gas, so if we change the pressure, it changes the volume. So we can substitute the ideal gas law, right? So we have RT over P for the molar volume, and we were going from the initial pressure P to some new partial pressure A, and we can pull out the RT because we already said that it was isothermal. So that's RT log of PA over P. Okay? So the difference in chemical potential as a gas expands is just this term RT log of the new pressure over the old pressure. And we can write a similar thing for component B. Without doing all the math, we'll just write it by analogy that the chemical potential of B mixed minus the chemical potential of B pure is the same thing. It's just RT log and the new pressure of the gas, the new partial pressure of gas B over the original pressure P. Okay, so let's go ahead and combine this with what we had on the previous page. So on the previous page, we had that delta G mix was just equal to NA delta mu A, right? This is mixed minus pure. And then the amount of B and the delta mu of B. Okay, so let's go ahead. We're calling this delta mu, right? How much mu changes when we mix. Okay, so if we plug those expressions, RT log of P in here, let's see what we get on the next page. We get the delta G mix was equal to the amount of moles of A, RT log of the partial pressure of A at the end of mixing over the original pressure, and then we have the same expression for B. Whoa, that's PB. Okay, there we go. And what we can do then is remember that we have two gases in the box at the end. Let me just draw that. And they're at different partial pressures, right? Because there were differing amounts of the two gases at the start. But at the start, the total pressure in the box was P. And that means we know that PA plus PB is equal to P. And so what we can do is we can say, aha, mole fraction. The mole fraction of A has to be equal to the partial pressure of A over the total pressure, and the same thing for the mole fraction of B. Right? The two pressures have to add to P. And once we do that, we can recognize that these are mole fractions up here in these logarithms. So we have NA RT log of XA plus NB RT log of XB. And the final thing we can do is we can divide each of these by the total number of moles, which means we have to multiply out here by the total number of moles. And when we do that, we get the total number of moles on the outside, and on the inside we get the mole fraction of A, log of XA, plus the mole fraction of B, log of XB. And that's a nice simple expression for delta G of mixing. Okay, and let's remind ourselves what we were deriving here. This is isothermal mixing of ideal gases. And not just they were at the same initial the initial pressure was the same. Okay, their final partial pressures were not the same, right? Because just to remind yourselves what it looked like at the start, we had differing amounts of A and B, and so this one spread out more than this one did. But their initial pressures were the same, right? Because remember, this is a movable barrier. So if we have gases at the same initial pressures, separated, and we allow them to mix, the delta G we get is this. And it turns out we're going to be able to adapt this to solutions, which is what we'll do in the next screencast.